We previously looked at gradient descent to optimize one parameter, specifically that being the slope of best fit for this data set, where we forced the intercept to be the point 0, 0. We really only did that just so that we could optimize with one parameter intact, namely the slope where we had b fixed to 0 in the equation y equals mx plus b. Remember that this is what we call our loss function. This is the sum of the squared residuals, which is the sum of the squared differences between the actual y and the predicted y. When the actual y and the predicted y are far apart, then this, what we call deviation, will be big, and if you square it, it'll make it even bigger, and if you add them all together, you'll get a really huge sum of squared residuals. And as we can see in our initialization, setting m equal to 1, we had really big residuals. These red bars represent the individual residuals before they're squared, and then once they get added together, it becomes large. The reason we square, at least one reason why we square, is because we could have positive and negative residuals, and those residuals could be really large, but they may sum to 0 just because of how they're placed. So to solve this problem, what we need to be able to do is now choose a intercept as well. And how do we do this with an intercept? Well, we still have a loss function, and we're going to call that loss function, instead of calling it SSR, let's just refer to it in general as L. Okay, it's some function. In our case, this loss function is the sum of squared residuals. Not all machine learning applications use the same loss function, so we'll generally denote this L. Now we want to optimize it with respect to some set of parameters, and that parameter can be a vector, or it could be a single value, like when it was just m. So in our case, this vector is going to be both m and b, and I'll label them sub k because they're going to be changing until we find the best mk and bk. It's going to be a very similar process, but now we have a vector for the slope and intercept, which is the theta sub k vector, as well as a gradient vector, which would be the gradient of the loss. In the case where it was just SSR, we had just one derivative, so we didn't really call it the gradient vector. It was just SSR prime or L prime. But now we're going to have the derivative of our loss function with respect to m, and the loss function with respect to b. So this vector will look like this. It will be in the top portion, since we're going to define this to have m and b in that order, we're going to have dl m, so the derivative of L with respect to m, and then the derivative of L with respect to b. And one thing that we need to recall here is that the gradient vector points in the direction of maximal change. So if we want to minimize something, we have to move in exactly the opposite direction. And so what we're going to do to our vector of parameters is we are going to subtract, because naturally, if you notice, this is the exact same formula, except now it's in vector form. We are actually subtracting because we want to move in the opposite direction. And remember, a gradient vector is a vector, and so if this guy is x, then negative x would be the same vector but pointing the exact opposite way. Okay, so we just want to move in the direction of the opposite of the gradient vector. So in order to do this, we are going to need to set up our loss function, which is going to look very similar. Don't be intimidated by this. This is just the actual y. And this right here is the predicted y from our regression equation with our current slope and our current intercept. Now I've added also this notation here that this summation is going to sum up all of the yi's minus the mk xi plus bk for each value of the slope and intercept, because our vector of x's was the set of points 6, 8, and 9, and then our vector of outputs corresponding to these number of hours of sleep of a variety of students, their GPAs were respectively 3.2, 3.5, and 3.9. And so each one of these elements, we typically subscript. So if we want to, how do we refer to the first element? Well, we just call it x1 without a vector on top of that, and this would be y1. And of course, then we have x2 and y2. So our summation notation, just to start at 1 and to go to n, in this case, n is equal to 3 because we have 3 components inside of the x vector and the y vector. But what this does is this essentially is adding or doing a subtraction involving the scalar component. So there'll be 3 terms to this summation, one for the pair 6, 3.2, and then 8, 3.5, and then 9, 3.5. Remember, the m and the b do not change when you're computing this. They only change when you update them. Okay, so what we're going to have to do in order to set this up is now our summation is going to involve taking, oh, I'm sorry, I should have put a squared here. I failed to do that. And now, in order to compute this, we're going to need, and we're not going to do this by hand. We're not going to do this in any application other than directly in Python, just because it's a little bit tedious, especially with having to update 2 parameters. But so that we understand the setup, we are going to have the derivative of the loss in order to form the gradient with respect to m, which recall that that's just going to be the sum. And again, as long as the sum is finite, meaning it's not infinite, you can take derivatives just like you do normally. Even for infinite sums, a lot of times you can, but anyway, beyond the scope of this conversation, we got 2 times yi minus m sub k xi, and then I'm going to distribute that negative just so that I don't have to write so many parentheses, minus b sub k to the first power. That's just the power rule, and then by the chain rule, we need to take the derivative of the inside with respect to m, sorry, with m sub k, I guess I should have said, and that means that the derivative of y will be 0. The derivative of this term with respect to mk will be minus xi, and then the derivative of b is going to be 0. Okay, so basically it's exactly the same formula. I'm just taking the individual derivatives. Now we'll have the loss function, the derivative with respect to b, which is a new one, but it's kind of the same thing. Just when we do the chain rule, we'll have to differentiate the inside stuff a little bit differently. We're differentiating with respect to b sub k, and that means that the derivative of the first term, y, is going to be 0. The derivative of the second term is going to be 0, and the derivative of the third term will be minus 1. So if you simplify this, it's really just negative 2 times this parenthetical expression, very, very similar. And then what we're going to do is we're going to take our starting guess. So let's say we initialize m0. I'll just say, because this is not required, but let's say m0 is 1 and b0 is 0. So this is just our starting value. It doesn't matter what we set those to. You don't have to make them 1 and 0. And so now what we're going to do is to get our next value of m and b, m1, b1, we're going to take our starting values of m and b, 1 and 0. We're going to subtract away learning rate. And for the sake of the conversation here, we'll just set the learning rate to something like 0.001. Remember, that's the learning rate. The bigger you set this, the more chance that you're going to get a lot of bouncing around and non-convergence. And if you make this too small, you might run out of iterations before you actually converge. And so now inside of here, we are going to have, I'm not going to rewrite the whole thing, but we'll have the derivative of L with respect to m0. Well, maybe I will go ahead and write it in just so you can see what the computation is. So it's just going to be the sum from 1 to 3 for both of these. The top one will be 2 times yi minus the value of n that we have, which is 1 xi minus 0, which is our starting value of b, times negative xi. Okay, so that's just going to require summing those together, calculating what that is. Down here, it'll be 2 times, negative 2, because we'll get that minus 1 there, yi minus 1xi minus 0. And that's it for that guy. So that's just going to be for this first computation. Once we get our new m1 and b1, the thing that will change in this computation will be, this will become m1 b1 once we're getting m2 b2, our next iteration, and then these, of course, will, the slope and the intercept will be the only things that change in here, which, of course, that means we will get a different sum of squared residuals. Okay, which means we'll get a different derivative for the sum of squared residuals. Now, if we want to execute this, right, and this is going to kind of keep on going until we get down to whatever happens first. We either run out of iterations or it converges. So let's go ahead and take a look at the Python execution of this. It's going to look a lot like the original code for just estimating one parameter. I'm just going to also import in here the capability of plotting 3D, have our SSR function. We now have two derivatives. We have the derivative with respect to m and the derivative with respect to b. Probably could have just called them dm and db just to keep it simple, but it's already in here. And also, it's not totally necessary to require both the x and y parameters as long as x and y are defined, but this is just a healthier way to do it in the event that the vectors or the lists of data change names. And so we have here, I've just, remember there's a multiplier of -1, so I've just made that -2. This negative came from the fact that it was the derivative of negative mx is negative x. And so again, we have our data, we have our initialization of parameters. It should not matter what you choose as far as the long-term convergence. Here I've chosen a learning rate of 0.001. I've had to tinker around with this actually because the sensitivity of the algorithm to the learning rate is actually pretty mind-blowing. And now we want to keep track of the means, the B's, the vertical intercepts, and the SSRs so that we can plot those later just to see the path that we're taking to get to that minimum. Finally, we'll just append the initial values of M, B, and SSR. And for now, I've actually updated this code a little bit. I am just going to continue to run this 100,000 times as opposed to requiring an SSR difference. So I'm just going to let this run. And basically the only thing that we're going to do differently here is I'm not vectorizing this right now. So the M and B's are, this is actually part of a vector, but I'm just doing it in the scalar form, just so I don't have to keep extracting and zipping up the ordered pairs into vectors and indexing and all that stuff. So here I'm just taking M minus the learning rate times the derivative of SSR with respect to M, B minus learning rate times the derivative of SSR with respect to B. Then we just append those values. This right now is not going to do very much, but let's go and take a look at what this executes. So we'll go ahead and run this cell. And so this is going to run quite a few times here, just to illustrate what's going to happen. We end up getting an M of about 0.22 and a B of about 1.84. If we now come up with the regression, just to visualize this, let's see what the regression would produce. So y1 tilde mx1 plus b. And so notice that we get a slope of 0.221 and 1.836. So how does that differ from what we came up here? Well, we got 0.221, 1.836. So pretty good. Actually very good. We came up with just the same values as we would in the regression. So we've minimized our loss function, and we've just continued to let this run as long as possible. Because I found after tinkering around with this process is extremely sensitive to the learning rate and how many iterations you allow. So if I just add one extra 0 and run this, let's see what takes place. So it'll still run through all iterations, and notice that we get slightly different results. 0.27, which is off from our 0.22, and 1.42 instead of 1.84. And that's also going to have to do with an interplay between the number of iterations and the learning size. If you decrease the learning size, naturally it's going to require more iterations to achieve that same value, because remember, this is scaling both slopes. In other words, it's scaling the gradient vector. And by scaling the gradient vector by something smaller, we're going to need more iterations for it to approach its final value. So let's go ahead and take a look at where we end up here. So here we started off with we picked an M of 1 and a B of 0. So that point looks to be here, looks to be this point here. And then we sort of descend down until we get a very small value of M and a very small value, well, not a big value of B, but a 1.84, which you can see is over here. So here's our path of convergence. And you can see as we try to rotate this, it's going to be a little bit tricky to rotate it just because there's so many data points there. But you can see how long it actually takes and how quickly it's already reached pretty much a 0 SSR. So the reason I did that as opposed to having a cutoff is because the SSR, even though it's nearly not changing anymore, even those small changes in SSR are actually creating some substantial differences in the M and the B. That's as opposed to this graph, which you can see all we have is same number of iterations, but our learning rate is much smaller. So it takes a lot longer to descend down versus here you can see we descend down pretty quickly and then just sort of linger in this range for quite a while. So the question is, and that's something that we're going to address here, how do you decide on step size and all of this stuff? There are different methods. We'll briefly look at something called stochastic gradient descent, and there's also gradient descent with momentum. There's various ways to do this, but the logic on a coarse grand scale is pretty much the same.